we need to be able to recognize the different types of limits and know how to work with each one. The first type, very easy. You are just going to substitute the value x approaches and simplify. X is approaching 3. So everywhere where there's an x, I substitute a 3. And the moment I substitute the value, this limit symbol disappears. And I simplify. 3 squared is 9, times 2 is 18, minus 3 is 15. The next one, it is now h approaching 0. So I'm going to substitute the 0 everywhere where I have an h. The x remains an x. I simplify. Anything times 0 is 0. So all that's left is 2x minus 5. So the answer won't necessarily be a constant value. The second type, if I substitute x is equal to 2, this denominator will equal 0, and division by 0 is undefined. So the first method cannot work. I have to make another plan. This plan is to factorize the numerator and the denominator. I'm not substituting any value yet, so I keep the limit notation. I factorize the numerator. That's difference of 2 squares. So it factorizes to x plus 2 times x minus 2. And now these two brackets can cancel out. And all that's left is the limit x approaching 2 of x plus 2. Now I can substitute. And the moment I substitute, the limit disappears. The third method, x approaching infinity. I don't know how to substitute that. When you see x approaching infinity, the other plan is to divide every term by the highest power. If you look at this algebraic expression, the highest power of x is x squared. And now I'm just going to do exactly what that recipe tells me. I'm going to divide every term by x squared. So x squared divided by x squared. And I do each term by itself and in the denominator. Now I'm going to simplify. I'm not substituting anything yet, so I keep the limit symbol. X squared divided by itself is 1. X can cancel out one of the x squareds in the denominator, and the last term cannot simplify. In the denominator, again, 3x squared divided by x squared is 3. And now I'm going to use a principle that I know if I have the limit x approaching infinity of 1 over x, that is equal to 0. Let's look at examples. If we have a half, value is 0.5. If I make that denominator a little bit bigger, 0.25 is a quarter. If I make it a little bit bigger once more, it's 0.125. So I can see as the denominator gets bigger, the value of the fraction gets smaller. So imagine if x approaching infinity, which is a very big number, this value will get almost 0. So I'm going to use this fact to simplify what I have here. So if I now substitute x is infinity, the 1 will remain a 1. This will approach 0. That will approach 0. The 3 will be 3. And if I have an x infinity in the denominator, it approaches 0. And I have a simplified answer of a third. We're now going to do one example where we use limits to apply differentiation from first principles. The formula for differentiation from first principles is the limit h approaching 0 of fx plus h minus f of x over h. If we're differentiating fx is equal to x squared, so we already know the value of f of x. We're now going to find the value of f of x plus h. That means it's x plus h squared, because the function we're working with is x squared. X plus h squared means the bracket times itself. And if you expand that and simplify, you get x squared plus 2xh plus h squared. And now we're going to substitute f of x and fx plus h into the limit. So the derivative of f of x is equal to the limit h approaching 0 x squared plus 2xh plus h squared, that's fx plus h, minus f of x is x squared over h. X squared minus x squared add to 0. Can I substitute h with 0? No, because it will give a denominator of 0. The plan I make then is to factorize. H is a common factor in the numerator. So there's left 2x plus h. If I now substitute, the moment I substitute, the limit notation disappears. It's 2x plus 0. So I now see that the derivative of x squared is 2x.